So I'm William Rawson. I'm a graduate research assistant in the Space Systems Design Lab, advised by Dr. Lightsey, and I am the systems engineering lead for the VISORS mission, which is a Two-CubeSat distributed telescope for coronal observation. Today we're going to talk a little bit about the science and engineering goals of this mission. So first we'll do a little bit of a detour, talk about SSDL and CubeSats for those of you that are not familiar. And then we'll talk about some of the science goals and how that motivates the engineering demonstrations that we're trying to do. And then hopefully we can conclude with maybe some takeaways and where we go from here. So what is SSDL? The Space Systems Design Lab here at Georgia Tech. We do all kinds of research, small sat technologies like this, also spacecraft navigation, life detection with Dr. Carr, if you guys are familiar with his work. And some examples of recent work, you may have heard about the two CubeSats we just deployed from the International Space Station. There's GT1 right there. I worked on that in undergrad. And then as an example of kind of the like end-to-end capabilities that we're trying to develop, this NASA Lunar Flashlight mission, we've been heavily involved. We provided a propulsion system that you see here. We also integrated and did the testing campaign for the satellite, and we're going to be operating that satellite as it orbits the moon searching for water ice. So what is a CubeSat exactly? Well, it started out as a purely educational endeavor by this design standard maintained by Cal Poly, but it's really exploded since then because it was adopted not just by educational institutions, but also by government and commercial entities. So that's really great for us educational institutions because it means we have all of these rideshare opportunities, all kinds of high-performance, commercially available parts that make missions fast and cheap, as well as lots of published research for resources starting off in design. And kind of the result of this is that we have a very compact, affordable form factor for space exploration. So that's kind of why CubeSats in general. So now specifically talking about VISORS, which is an acronym for Virtual Super Resolution Optics with Reconfigurable Swarms. So the science goal, or we'll start off with a bit of an overview, is funded by the National Science Foundation from their CubeSat Ideas Lab in 2019. They brought together a bunch of industry professionals and had them kind of come up with these crazy ideas to really push the boundaries of what was possible. This is one of those missions trying to further knowledge of the solar corona via this distributed telescope concept. And so in addition to kind of the science goals, the demonstration of this kind of precise formation flying is a very exciting engineering goal for us. And as far as the status, we've passed critical design review. So we're currently fabricating hardware, getting ready to integrate and test, hopefully launching early 2024 around solar maximum. So this is like the formal statement of our minimum mission success science goal. We're gonna try to build this up a little bit more. But in observing the corona using this distributed telescope, not only will we hopefully be able to observe some different phenomenon in the corona, but we will also demonstrate key formation flying technologies. So we're going to talk a little bit more about these in turn. And then the other goal, in addition to all this engineering and science, is education, and that's a big priority of NSF. So this could also be seen as kind of an acknowledgement slide. I am a very small part of this huge mission. There are partners at all these educational institutions, and part of the purpose of that is to educate and train the next generation of engineers and scientists by interacting with colleagues and also with professional engineers and scientists at places like NASA Goddard and the Laboratory for Atmospheric and Space Physics in Colorado. So starting with the science goal, which you could state as to achieve unprecedented resolution in coronal imagery. But why do we care about this? Why do we want to do this? So we're trying to answer the question of how is the corona heated? So the surface of the sun is very hot, then the temperature drops off relatively low. It's still very hot. But the corona is way hotter, and that's where you get all the space weather, coronal mass ejections and stuff like that. So if we can understand how all this really rapid heating happens right here, we might have a better understanding of space weather. But the problem is that the current hypothesis is that this heating happens in localized regions on incredibly small scales. 100 kilometers, not very small. But when you observe 100 kilometers on the sun from Earth, you're looking at something that is 1/24,000th of a degree. So the problem with that, as shown in this image, is that it's beyond our current capabilities. So this is an image of the solar corona, 0.6 arc seconds. So you have to increase that by like a factor of 4 in order to observe these structures. And you can kind of see what might happen when you do that is kind of these images here. So we're trying to get somewhere in here. So how do we achieve this resolution? The first thing to know is that we want to observe in the extreme ultraviolet wavelength because that's where ionized helium emits the best. But the problem is that these are very small wavelengths compared to like the infrared wavelengths that James Webb uses. So we can't use, at least it's not practical to use mirror-based optics. We just can't manufacture them to the high enough tolerances in these small wavelengths. And so what do we do instead? We can use what's called a diffractive optic. So it's the one we're using is a photon sieve developed at NASA Goddard. It's based on the Fresnel zone plate. And this creates an interference pattern that is then post-processed to create an image. And the result is that we get this diffraction-limited resolution, which we need to observe these structures in the corona. So this is all great. We have the technology, but the problem is the focal length of this sieve is 40 meters, which is huge. It's the size of the space shuttle. So rather than spending hundreds of millions of dollars to build one satellite to hold this photon sieve, there's other solutions. So how do we create this 40-meter telescope? We can use formation flying with CubeSats, specifically a two-CubeSat formation. So the optics spacecraft up here, this is not quite to scale. These are like briefcase-sized, and then again like space shuttle distance. So the optics spacecraft holds the photon sieve, and also the solar panels block kind of stray UV light. And then the detector spacecraft has what's basically our camera. But the problem, again, now that you've put these on two separate spacecraft, that's great, but now you have to actually form the telescope. And there's a lot of kind of different requirements that go in here, but the thing that I want to emphasize is that we're looking at millimeter level tolerances in pretty much every direction and in the velocity. So millimeter level control of these two systems that are orbiting around the Earth. So the question of formation flying is kind of how do we do that? So first, to align them, you can't just necessarily rely on your orbital plane pointing towards the sun and then they just kind of follow each other around. That's not very flexible. So in order to obtain the targeting that we want, we have to use what's called a relative orbit. So this is kind of an example here where the one spacecraft is at this little dot, the other one, in a relative sense, orbits around. So you can produce alignment towards the sun, and you can recalculate this trajectory to obtain any alignment you need towards the sun. But what is a relative orbit exactly? It's not quite the spacecraft orbiting each other. They're still orbiting the Earth, but they're doing so in very slightly different orbits, so that if you say, okay, forget about the fact they're orbiting the Earth, and just say that this one spacecraft is the origin here, it's not moving, and you just look at the relative motion, they can kind of appear to orbit around another. And the nice thing about this is that you can linearize these equations of motion, which has great implications in control, as we're going to get into. So this is an example of kind of the different trajectories we can accomplish with this relative orbit. So we can design trajectories to have different purposes, this kind of standby, relaxed trajectory, and then when we want to do science, we go into this tighter orbit. But how do we actually get there? How do we make sure we stay on track? Because there's other disturbances, there's solar radiation pressure and atmospheric drag. So how do we actually maintain that orbit? And that is the question of guidance, navigation, and control. So we're going to talk about these one at a time, but this is maybe the better order, is navigation, guidance, and control. But that's not how people ever say it. So starting with navigation. So how do I determine my position and velocity? The nice thing about being in low Earth orbit is that you're still below the GPS constellation, so you can use GPS, which is great, but GPS, quote unquote, only provides meter level accuracy, which is really good, but again, it's not good enough. We need millimeter level accuracy. And it turns out that the key here is that we need millimeter level accuracy in the relative position. And the relative is really key because we don't care necessarily as much where we are relative to the center of the Earth. So we can use a technique called differential GPS, which has been applied on Earth for things like aircraft, like you can see here. And the basic concept is the errors in GPS vary spatially. So if you know your correct position, you can kind of correct your GPS measurement and then broadcast those corrections, and other users can get better accuracy. So we're kind of abstracting that concept and say, well, we don't exactly know our exact position, but we know these two things are close together. So we know the errors have to be similar. And so you can kind of use the subtraction of the two measurements to provide millimeter level accuracy. And specifically, we use this algorithm developed at Stanford. They're one of the partners on this project called Digital. But again, the challenge here, this has to happen autonomously. We can't be sending information back and forth to the spacecraft. They have to talk to each other. So how do we enable them to talk to each other? Well, we have what's called an inter-satellite link. And this has to be omnidirectional. We can't rely on exactly how they're being pointed because, again, they're orbiting around each other. So we have these patch antennas on every face of the spacecraft. We have a second dedicated radio, not for space-to-ground communication, but for, you could call it space-to-space communication. And that enables them to share the navigation data that they need in order to provide this millimeter-level accuracy. So that's the first kind of key enabling technology, or you could think about it as the pair, is the navigation algorithm and this inter-satellite link. So we know where we are, but what if we're not where we want to be? Or what if we need to change where we are? So we're in this standby orbit, which is great for downlinking data, but we need to go do science. So how do we do that? We have to calculate a trajectory, which would involve a maneuver plan. So this is the problem of guidance. And we can actually use the fact that we can linearize the relative equations of motion to do this very easily. And you can actually pose it as an optimization problem, which is what we do on VISORS. So there's an onboard convex optimization solver that is solving these constrained problems to minimize our propellant consumption and also subject it to the constraints of our propulsion system, because it can't do everything. So we know what it can do, and we're able to minimize how much propellant we have to expend. And you get this so you have this blue trajectory, and it calculates all your little maneuvers to get there. You can also use this for control. So if you're in this red orbit, you can use it to stabilize and make sure that you don't leave the orbit, for example. So this is another enabling technology, is these optimal guidance algorithms. So this is great. We have all these maneuvers. We know what we need to do, but how do we actually do it? So obviously, use thrusters, been done on spacecraft forever, but they're very complicated. They require pressure tanks and valves and explosive propellants that are highly toxic, right? Which is not great for CubeSats, especially if you're on part of a larger launch vehicle. They don't like that. So what we do is we 3D print propulsion systems. And this is something that we've done several times at Georgia Tech, and we use what's called cold gas. So in this case, it's actually a refrigerant that's relatively non-toxic. And the great thing about this is we can fit it into these small irregular volumes. We've got all these other important science and mission payloads, and we can kind of cram it into the bottom here because we're 3D printing it. And it really gives us a lot of performance, things that wouldn't have been possible in a CubeSat form factor before. So this miniaturized propulsion is another enabling technology that we're demonstrating here. So now we can put it all together. We have relative navigation with meter level accuracy. We have guidance algorithms to figure out how to get where we need to go. We have this miniaturized propulsion system to get us there. And so these form kind of the key formation flying enabling technologies that will allow us to expand what we can do in a CubeSat form factor. And where do we go with this? So, maybe in the context of kind of exploring the universe around us, one potential application is observing exoplanets. So they're very hard to observe because they're very dim compared to the stars that they orbit around. So one concept that's being explored is this kind of star-shade telescope combination. So you would fly in formation. It would work a little bit differently. You'd be a lot further away. But this giant star shade would block out the light of the star, allowing the telescope to observe exoplanets kind of along the fringe. So that's one potential application. There's others in kind of these swarm concepts where instead of getting like one measurement from your instrument per 90 minutes as you orbit around, you could have a string of them, and you can maybe get like one every minute for like a 10-minute period or something like that. So takeaways, we're trying to enable groundbreaking resolution in coronal imagery to analyze heat release regions in the sun. And if we succeed in this goal, we will also be demonstrating several key formation flying technologies. And in terms of the bigger picture, this is really exciting because if we can meet these really ambitious goals, if we can do better than these $100 million solar observatories in a like singles of millions of dollars budget, it's a really interesting paradigm that will enable NASA and NSF and other partners to really strive for some more ambitious goals, which is already happening. There's a lot of NASA CubeSats that are doing really exciting science, and that's kind of the really interesting paradigm here. And again, I just want to emphasize, I stayed pretty high level here to kind of introduce you to the mission, but we've designed all the hardware, and we're working to build and test components right now, which is very exciting. Yeah, that's all I have, so I'd be happy to answer any questions.
I think we've got time for one question for William. Oh, awesome.
So why is formation flying an easier solution than using something like cables?
So tethers are an option. Yeah, tethers are an option, but they're kind of less flexible in the sense that, like, once you're kind of orbiting each other around the tether, it's a little more difficult to change the way in which you're orbiting to align in a different way. So you would still need to be able to, for example, control your position to like millimeter level accuracy, because the tethers are, I said they're not flexible, but they are flexible is the problem too, right? So you're going to get bending and warping. So that is an option, and it's something that people have explored, but it kind of hasn't gained as much traction because you still run into the same problems with having to figure out where you are and needing to be able to actuate yourself to change where you're pointing and stuff like that. But that definitely is an option, and there are people that are looking into doing CubeSat swarms with tethers and stuff like that.
Awesome. Thank you so much.